Hi there! Our project is named Autonomous Underwater Diver Assisting Robot, or for short, UDAR. We have worked under the supervision of Dr. Pompelli, and we would also like to thank Mr. Rehmati for his support. We are Team 46 for Capstone, and my name is Parth Kumar Patel. These are my teammates: Syed Hussain, Nilay Patel, Smeet Kathiria, and Tanvin Patel. Underwater diving is a sport that can be enjoyed by everyone. The sea creatures and mysterious world that lie underneath the ocean are just some of the things that make diving interesting. While diving is a fun sport, with it comes diving fatalities. In the article from Diver Annual Diving Report 2018 edition shows the report of 2016, which shows that there were 169 diving fatalities, injuries, and incidents reported to DAN. Another article, Fatalities, Inexperience a Big Factor, reported approximately 100 divers dying in the United States and another 100 divers dying in the rest of the world each year. According to these articles, the major cause of the diving fatalities were due to equipment malfunction, cardiac condition, and drowning. Our project, Autonomous Underwater Diver Assistant Robot, focuses on making the diver's experience go smoother and helps reduce underwater diving fatalities.
You might have seen drones that track and record cyclists and runners. However, the things become more demanding when working underwater. One of the challenges we would face was the clarity of the live feed captured by the camera. The underwater environment is muddy and unclear, therefore performing detection and tracking is difficult, unlike above water. To resolve this issue, efficient algorithms and sensors are required.
Another challenge was understanding and finding a solution for GPS communication with the Blue Rover underwater. As we know that there is no GPS underwater, we had to think of a way to settle this challenge as well. Additional challenges that came to light were the energy consumption and processing power on the Blue Rover. To maneuver the robot and to perform video processing, the Blue Rover requires sufficient power. Due to the limited power supply on board, adding larger processing units would increase the power consumption, which would make the robot to become too heavy and harder to maneuver. Hence, to sort this challenge, we implemented a suitable design.
Blue Rov is an underwater robot that is very capable and modular in design. The main reason we choose to work with it is that it is open source and is widely used for research purposes. The design consists of 6 thruster, an HD camera, and a lot of onboard sensors, while the data processing and flight controls are handled by a Raspberry Pi and Pixhawk flight controller. The Blue Rov also has a Fathom Rov tether attached to it, which is the yellow cable, designed specifically for remotely operated vehicle ROVs. In our project, tether is used to transmit and receive data while enabling live HD video streaming, which makes it an autonomous underwater vehicle, for short AUV.
We have implemented our project using the Blue Rover robot with the capabilities of tracking, detecting, and following a diver at an appropriate distance. While underwater, the robot will be able to detect different objects, divers, and hand signals provided by divers. Hand signals are used by divers to communicate with each other while underwater. Similarly, we have trained our robot to understand those basic hand signals to automate the communication with the person on the surface. Using Robot Operating System, or simply ROS, we have controlled the Blue Rove's movement to follow the diver. We have implemented basic movement for the robot in a simulation environment.
Our project design uses a Blue Rov, a buoy, and an on-surface computer. Blue Rov is used to capture the live feed of the diver and follow the diver wherever he or she goes. It is connected to a buoy through a Phantom ROV tether, which is used for data transfer in our case. The buoy acts as the powerhouse of our project. The main function of the buoy is to act as a communication bridge between the Blue Rov and an on-surface computer. Furthermore, This design would help us resolve the energy consumption, processing power, and navigation problems. We have added a NVIDIA Jetson TX2 kit, which is an embedded AI computing device that is power efficient and gives exceptional speeds for our computation. On top of that, it also aids the GPS communication between the robot and the buoy. The on-surface computer receives the live feed captured by the BlueRov and gets the information required by the people on the surface. We divided the project into two subparts: computer vision, deep learning, and robotic operations using ROS and Arduino.
We have made use of modern tools and technology such as Python, OpenCV, and NVIDIA Jetson TX2 to implement the computer vision and deep learning part of the project. Object detection is used for detecting the diver and their hand signals. We have modified and made use of a real-time object recognition algorithm, YOLO, to identify divers and their hands and other objects. To help divers communicate with the person monitoring above water, we have made use of hand signals commonly used by divers. The hand signals we have implemented are up, OK, stop, and down, as they are the most static signals of all the hand signals. We have also implemented algorithms that track hands in the frame and assign a unique ID to each hand detected. Using the ID assigned to the hand, we are able to track left swipe, right swipe, and any distress signals that are given by the diver.
To understand the performance of the hand signal classifier algorithm, we formed a confusion matrix. Confusion matrix provides an insight on how the classifier is confused when making predictions and inform us about the errors being made. From the testing dataset of total 346 different hand images, the classifier correctly identified 244, which gave us an overall accuracy of 70.5%. The accuracy we obtained for classifying hand signal isn't outstanding yet, but it can be improved with using more label training data. Since the accuracy alone doesn't provide a complete picture about the performance, therefore with the use of confusion matrix, we evaluated some more performance benchmarks such as precision, recall, and F-score to further understand the performance of the classifier. Any individual performance metric cannot clearly determine the performance. Therefore, we combined those and created a precision recall curve and a ROC curve. The precision recall curve provides information on the trade-off between positive prediction value and true positive rate for the classifier with the different probability thresholds. And the ROC curve summarizes the trade-off between false positive and true positive rate for the classifier with the different probabilities.
ROS is a robot operating system which has a flexible framework for writing robot software. It facilitates communication between sensors and motors in a well-structured fashion and adds many facilities for communication. For example, controlling robots from other machines. Our decision to use ROS was based on the fact that there are ample libraries and packages that can be integrated in the project to help ease the burden of creating new functions and framework. The other component of the project is controlling. We decided to use ROS to implement the automation on the BlueRov. We implemented and modified a couple of packages to work with our project to control the BlueRov hardware. Following packages were used: Free Floating Gazebo, JoyNode, MavROS, and Mavlink packages to transfer the messages from one node to another node. However, after compiling those packages, there were quite a few errors in almost all the packages found on GitHub. Those packages were fixed by going through them line by line, but we had to move to a simulated environment due to the current pandemic.
Softwares like Software in the Loop, Arduino and Mavlink were used to run the simulation. This software allows us to communicate with the robot without any hardware. QGround Control provides full flight control and mission planning for any Mavlink enable hardware, so we used that to do the simulation. ArduSub is used to open the BlueRAW, and QGround control is used to add the predefined path using Path Planner. Path Planner is a mission that we run that has a set of directions that we give to the BlueRAW so that it moves in the given direction. The BlueRAW will then follow the instructed path. Since this is just a simulation, functionality of object detection and following the object using the BlueRAW camera is possible on a physical hardware. As you can see in the BlueRAW simulation, the BlueRAW ends at the instructed path which we give in the software.
Overall, it was an ambitious project with many challenges. While some of the challenges were resolved, there were still some that could be explored and worked on in the future. Better algorithms can be implemented to increase the accuracy of the detection. Our project only implemented 4 hand signals as they were the most static ones, but more hand signals can be incorporated, including non-static signals. Implementing additional hand signals will provide more ways for the divers to communicate with the person above water. Further, the hand signals can be used by the diver to control the direction of the robot. ROS was challenging to work with as it took some trial and error and some debugging to get it working as we desired. Furthermore, the libraries are useful when it comes to the benefits of ROS. Moreover, ROS can be explored even further to enable different features of the BlueRAW. Finally, we enjoyed working in the challenging environment and under excellent supervision from Dr. Dario Pompelli and Mr. Mehdi Rahmat.